Hi gents. Let's learn how to size a pump for the standpipe and hose system. First we will see how to size for pump discharge. Parameters to be known are: class of fire hose cabinets, number of risers. Procedure of calculation is as follows. For Class 1 and Class 3 systems, the minimum flow rate for hydraulically most remote riser shall be 500 GPM. The minimum flow rate for additional risers shall be 250 GPM per riser, the total not to exceed 1250 GPM. For Class 2 systems, the minimum flow rate for hydraulically most remote riser shall be 100 GPM. Additional flow needs not to be added when more than one riser is provided. Example: a building of 5 floors is provided with 6 Class 3 fire hose cabinet risers. Each riser is connected to one fire hose cabinet in each floor. The required discharge for the fire pump is 500 GPM required for the most remote riser, 250 GPM required for each riser of the other 5 risers, so total required discharge equals 500 plus 1250 equals 1750 GPM. Since total not to exceed 1250 GPM, then pump discharge should be selected at 1250 GPM. We will move to size the pump head. Parameters to be known are: class of fire hose cabinets, the height between the pump discharge and the highest fire hose cabinet, pipe material, pipe horizontal and vertical length from the pump discharge to the most remote fire hose cabinet, each diameter separately should be measured. Valves and fittings equivalent length. Discharge flow. Procedure of calculation is as follows. The residual pressure at the outlet of the hydraulically most remote hose connection should be 100 psi for Class 1 and 3 and 65 psi for Class 2. From Table 8313 from NFPA 14, we can calculate the equivalent length of valves and fittings. This table should be used where Hazen-Williams C factor is 120. For other values of C, the values in this table shall be multiplied by the factors indicated in Table 8322. Hydraulic calculations and pipe sizes for each standpipe shall be based on providing 250 GPM at the 2 hydraulically most remote hose connections on the standpipe, as per NFPA recommendation. Pipe friction losses shall be determined on the basis of the following Hazen-Williams formula, where P is the frictional resistance in psi per foot of pipe, Q is the flow in GPM, C is the friction loss coefficient, D is the actual internal diameter of pipe in inches. Example: calculate the head of a fire pump if the most remote and highest outlet is a fire hose cabinet Class 1. The height of the cabinet is 20 meters from the pump discharge pipe level. Consider steel pipe of C value 120. The piping route from the pump to this most hydraulically remote unit is 60 meters of 6-inch diameter pipe with 1 gate valve, 1 check valve and 3 90-degree elbows. The flow is 500 GPM, which is the required 250 at each of the 2 remote connections. And 4 meters of 6-inch diameter pipe with 1 90-degree elbow of discharge, 250 GPM. Solution is as follows. Pump head equals static head plus residual pressure plus pressure losses. Static head equals 20 meters equals 29.4 psi. Residual pressure equals 100 psi, being Class 1. Pressure losses. For the 6-inch diameter pipe with 500 GPM, For the 6-inch diameter pipe with 250 GPM, therefore, the total pump head equals 29.4 plus 100 plus 2.61 plus 0.07 equals 132 psi. In this lesson, we are going to learn how to size the pipe network of a standpipe or fire hose system. Here you can see a typical wet standpipe system. Before we start, let's recall two important theories we learned in Lesson 1. First, for Class 1 and Class 3 systems, the required flow for hydraulically most remote riser is 500 GPM. And all other risers shall be 250 GPM per riser, with total flow not to exceed 1250 GPM. Second, for Class 2 systems, the required flow is 100 GPM, no matter how many riser we have. The easiest way to size the piping system is to use Table 7821 below, which was extracted from NFPA 14 2003 edition. From this table, knowing the water flow and the distance from furthest outlet connection, you can select the pipe nominal size. Let's see an example. We have here a building with 6 Class 3 fire hose connection risers. I will start the sizing of risers first, then I will size the main pipes connecting the risers. Given below the distance from the pump to the most remote outlet on each riser. Solution is as follows. For riser F, the flow is 500 GPM, being the most remote riser. The length to most remote outlet is 290 feet. So from the table the required pipe size is 6 inches. For riser E, the flow is 250 GPM, which is the flow in all risers other than riser F. The length to most remote outlet on riser E is 240 feet. So from the table the required pipe size is 6 inches. For riser D, the flow is 250 GPM. The length to most remote outlet on riser D is 190 feet. So from the table the required pipe size is 6 inches. For riser C, the flow is 250 GPM. The length to most remote outlet on riser C is 140 feet. So from the table the required pipe size is 6 inches. For riser B, the flow is 250 GPM. The length to most remote outlet on riser B is 90 feet. So from the table the required pipe size is 4 inches. For riser A, the flow is 250 GPM. The length to most remote outlet on riser A is 40 feet. So from the table the required pipe size is 4 inches. For the main pipe feeding all risers, the flow is the sum of 500 GPM in riser F and 250 GPM in each of the other 5 risers. So the total is 1750 GPM. But since the total not to exceed 1250 GPM, then 1250 GPM to be considered. No matter the pipe length, the size should be 6 inches as per the pipe schedule table. Now, because the pump main is 6 inches and riser F is 6 inches, then all main pipes in between, highlighted in red, shall be 6 inches. Thanks for listening. And don't forget to subscribe for future videos.
Sprinkler systems. Before diving in the sprinkler system, let us go through some basic information related to firefighting. The fire triangle. The fire triangle is a scientific principle that is important for all people to be aware of. Understanding how fires sustain themselves is essential background information in situations where you may have to use fire safety equipment. The fire triangle, or combustion triangle, is the 3 components needed to ignite and sustain a fire. The 3 ingredients of a fire triangle are heat, fuel and oxygen. First, a source of heat is required for ignition to occur, and different materials have different flash points. Flash point is the lowest temperature at which the material ignites. Second, a fire cannot begin if there is no material to burn. Homes and businesses are full of flammable materials such as paper, oil, wood, and fabrics. Any of these can serve as a fuel for a fire. Third, to sustain the combustion reaction, oxygen is needed, as it reacts with the burning fuel to release heat and CO2. Earth's atmosphere consists of 21% oxygen, so there is plenty available to trigger a fire if the other 2 components are present. Fire blankets and certain fire extinguishers remove the oxygen side of the triangle by removing it or displacing it, causing suffocation, and thereby ceasing the combustion reaction. So, here are some facts about the fire triangle that we should keep in mind. Normal air contains 21% oxygen. Fuel may also contain oxygen. Heat sources include the sun, hot surfaces, sparks, friction, and electrical energy. Fuel sources can be a solid, liquid, or gas. Firefighting systems are classified either manual or automatic. Manual firefighting systems includes extinguishers, fire cabinets, Siamese connection, and fire hydrants. These requires the physical intervention of manpower to fight the fire. Automatic system, as its name says, fights the fire automatically without the intervention of human being, and that what a sprinkler system do. Here is a schematic diagram of the system components. Usually both systems exist in all buildings to form a competent firefighting system matching the NFPA standards. So, in any building, the system consists of 3 basic parts. A large store of water in tanks, either underground or on top of the building, called fire storage tanks. A specialized pumping system. This usually includes 3 types of pumps: jockey pump, electric pump, and diesel pump. You can refer to my video about fire pumping system for more info. A large network of pipes ending in either hydrants or sprinklers. Nearly all buildings require both of these systems. Sprinkler systems. When it comes to the sprinkler head itself, the 4 most common styles of sprinklers are the standard spray upright, standard spray pendant, sidewall sprinkler, concealed sprinkler head. Nearly all fire sprinklers are composed of the same components: a sealing assembly or plug that prevents water from escaping, a heat-sensitive element that allows water to flow at a given temperature, a deflector that distributes water effectively, and a frame. The sprinkler's temperature rating is the temperature at which the sprinkler will activate. Options range from 135 to 650 degrees Fahrenheit. These ratings can be identified by the color of the liquid inside the bulb in the case of glass bulb sprinklers. The selection is taken from NFPA 13 Table 7241 based on the hazard class for the structure that the fire sprinkler system is protecting. Upright sprinkler head. Upright fire sprinklers spray water upward to a concave deflector, like an umbrella, producing a dome-shaped spray pattern. Rather than descending through the ceiling, these sprinkler heads are usually mounted on pipes just below the ceiling. Upright sprinkler heads are efficient at dispersing water between obstructions. Thus, they are frequently used for rooms that are inaccessible, such as mechanical rooms and in warehouses and industrial spaces. They are also often applied in structures with open ceilings. The pendant fire sprinkler head. It is the most common type that you will see. Pendant sprinkler heads descend from the ceiling with a convex, circular, gap deflector plate on the bottom. When the sprinkler heads activate, they send a stream of water downward onto their deflectors, which then disperse the water widely, side to side, throughout the room in a conical pattern. Sidewall sprinkler heads protrude horizontally out of the wall parallel to the floor, rather than descending from the ceiling or mounted on a pipe pointing upward. Sidewall sprinklers are ideal for small spaces, such as hallways, spaces with obstructions, and where ceiling piping is not available. Concealed sprinkler head. This heat-sensitive plate detaches at temperatures roughly 20 degrees lower than the fire sprinkler head, allowing the concealed sprinkler's deflector to drop and the head to activate. Now we have covered the most common sprinkler head types. Let's go ahead and discover the fire sprinkler system types. There are 4 main types of systems: wet pipe system, dry pipe system, pre-action system, and deluge system. Wet pipe sprinkler systems. Here are the components of a wet sprinkler system. In addition to the water supply, piping, and sprinklers, these systems have backflow prevention device, control valve, main drain, fire department connection, water flow alarm. Wet pipe sprinkler systems always contain water in the riser and piping. As soon as a sprinkler head activates due to the heat of a fire, water is immediately discharged through the open head. Dry pipe fire sprinkler systems. Dry pipe systems are very similar to wet pipe systems with one major difference. The pipe is not constantly filled with water. Instead, the water is held behind a dry pipe valve, usually some distance away from where the sprinklers are located. Like a wet pipe system, when the temperature at the ceiling becomes hot enough, the glass bulb or fusible link of the sprinkler breaks. However, in this case, water isn't immediately available because the pipe is not water-filled. Instead, air is released from the now open sprinkler head. This creates a drop in pressure, causing the dry pipe valve to open and water to fill the system. Water will then flow from the open sprinkler head. Since there is a delay between sprinkler operation and water flow, the size of dry pipe systems is limited. The size limitation is intended to minimize the amount of time water delivery is delayed. A dry pipe system is a great option for unconditioned spaces, or locations where the temperature of the space cannot be guaranteed to be high enough to prevent water in the system from freezing. Pre-action system. A pre-action type sprinkler system employs the basic concept of a dry pipe system in that the sprinklers are closed and water is not normally contained within the pipes. One difference, however, is how water is admitted to the system. Water introduction into the system's piping is initiated by opening of a normally closed, mechanically latched valve known as a pre-action valve. Means of operating the pre-action valve depends on which of the 3 types of pre-action systems, non-interlock, single interlock or double interlock, is installed. Pre-action valve operation is dependent upon one or two of the following events occurring: sprinkler activation and detection device activation. A non-interlock system requires only one of either event to occur before water is admitted into the system. A single interlock system is activated only upon the event of detection device activation. However, in a double interlock system, the 2 separate events must happen before water is admitted into the system: sprinkler activation and detection device activation. Deluge systems are similar to pre-action systems in that they use another type of detection for operation. However, the biggest difference is that deluge systems use open sprinklers or nozzles. Instead of getting water flow from individual heads that have operated, once water fills the system, water will flow from every sprinkler head. Much like a pre-action system, a deluge valve will keep water from filling the system until the operation of another type of detection system, such as smoke detection. Once the detection system is activated, water not only fills the system, but flows from the open sprinklers or nozzles. An important consideration in the selection of the type of sprinkler system is the level of hazard being protected. If protecting an area of very high hazard, such as aircraft hangars, a deluge system may be the most suitable. Automatic sprinkler system design. The layout of fire sprinkler systems is usually one of the following. Tree sprinkler system. It is the normal design system and it consists of main pipeline with branches on both left side and right side. Grid sprinkler system. A sprinkler system in which parallel cross mains are connected by multiple branch lines. Looped sprinkler system. A sprinkler system in which multiple cross mains are tied together so as to provide two paths for water to flow to an operating sprinkler and branch lines are not tied together. The maximum area of coverage per sprinkler head depends on hazard classification and sprinkler mounting orientation, that is, sidewall or overhead. Sprinkler head spacing. The table below shows sprinkler spacing requirements based on NFPA 13. For example, in a light hazard office area, the maximum coverage area per sprinkler head is 200 square feet, and the maximum design spacing between sprinklers is 15 feet. The maximum distance of sprinkler head from wall is half of the maximum distance between sprinkler heads. Minimum distance between sprinklers is typically 6 feet. Let us take an example: an office area of 90 by 60 feet. Assume we want to design a tree sprinkler system. Let us go ahead and lay out the piping system and sprinkler heads. Being a light hazard, the maximum spacing between sprinklers is 15 feet. The distance between sprinklers and walls is no more than half than the distance between sprinklers. The water demand for firefighting sprinkler systems shall be determined by either the pipe schedule method or the hydraulic calculation method. According to NFPA 13, pipe schedule system is defined as sprinkler system in which the pipe sizing is selected from a schedule that is determined by the occupancy classification and in which a given number of sprinklers are allowed to be supplied from specific sizes of pipe. Since our space is considered light hazard, and having no more than 2 sprinkler heads on each branch, then the size of all branches is 1 inch. For the main line, always start from the end. This portion is feeding 4 sprinkler heads, then its size should be 1.5 inches. This portion is feeding 8 sprinkler heads, then its size should be 2 inches. And all the rest are 2.5 inches because the number of sprinkler heads is more than 10 and less than 30. Now, what is the minimum water supply requirements for pipe schedule systems? The table below summarizes the minimum water flow rate, residual pressure, and duration of pipe schedule systems. Therefore, 500 GPM multiplied by 30 minutes means a minimum of 15,000 gallons water tank shall be constructed. A breakout of a floor control riser assembly. The following is a full arrangement for a combination standpipe sprinkler riser where high pressures necessitate a pressure-reducing valve at each level. While every element in this specific arrangement is certainly not a necessity on every project, here's some considerations that go into the requirements and considerations for a layout like this. Auxiliary drain valve. Permits faster draining of system, as opposed to only draining inspector's test valve. Check valve. Can help reduce false water flow alarms on floor where sprinklers have not activated. Drain pipe. Size, 3/4 inch for 2-inch system pipe, 1¼ inch for 2.5 to 3.5 system pipe, or 2 inch for 4-inch system pipe. Drain valve. Minimum size, 3/4 inch for 5 to 50 gallon system, 1 inch for above 50 gallon system. Drain riser. Discharge must be to outside or drain capable of handling the flow. Size must be at least one pipe size larger than the largest drain connection tying into it. Inspector's test. Must be accessible and must discharge outside or to a drain capable of handling flow. Must be downstream of water flow alarm. Pressure gauge. Required at each floor control valve. Pressure reducing valve. Provided to reduce the system pressure such that the working pressure will not exceed a standard 175 psi listed pressure of the sprinklers, piping, and fittings. PRVs can also be used to limit the system pressure to higher amounts when pressures are allowed to exceed 175 psi. Control valve for entire riser is required to permit isolating a riser without interrupting other systems. Size of minimum 4 inch, unless hydraulically calculated to permit smaller size. Sight glass enables easy verification of water flow for inspector's test. Floor control valve. Must be accessible, electrically supervised or locked. Signage must be provided and shall be tested annually. Water flow switch is used in wet sprinkler systems to detect the flow of water and to send an alarm signal. Zone control valve. Zone control valve is a combined unit of 4 parts: signal butterfly valve, water flow indicator, pressure gauge, and test and drain valve. They are assembled on fire pipeline to separate the fire area into small distribution zone for indication and control. Because of fire sprinkler or test valve activation, the indicator detects water flow and transmits signal to control system. After fire suppression, butterfly valve gets signal and shut down the water flow for recovering the system. A fire department connection, FDC, is a connection through which the fire department can supplemental water into the sprinkler system, standpipe, or other system, furnishing water for fire extinguishment to supplement existing water supplies. FDCs are required on all standpipe systems per NFPA 14, standard for the installation of standpipe and hose systems, and sprinkler systems per NFPA 13, standard for the installation of sprinkler systems. This connection is installed outside the building, usually on the exterior wall in order to ease the access of fire department personnel to it. Let's go inside and see where water flows when connected to it. As you can see, the pipe is connected to a standpipe. From this pipe there is one branch going to feed the landing valve, which I will show you later. Another branch is connected to the sprinkler system, as you can see. There are 3 common reasons why this additional water supply may be necessary by the sprinkler system. A closed valve on the domestic water supply leading to the sprinkler system. Inadequate domestic water supply being delivered to the sprinkler system. A change to the occupancy of the building that presents a hazard greater than the sprinkler system was designed to handle. Let's go back to the branch feeding the landing valve. In this design, as you can see, there are 2 connections going to the cabinet. One-inch pipe is connected to this fire hose reel. This will be used by the property-trained personnel in case of small fires. The larger connection, which is 2½ inches, is connecting to the lower cabinet part where the landing valve is located. This valve will be used by the firefighter. Here are the 2½ inches hose and its accessories. Hi gents! In today's video, I'll go through 2 of the most used pumps in HVAC industry. End suction pumps and split case pumps. End suction pumps are single suction, that means the fluid enters the impeller from one side only. End suction pumps can either be closed or flexible coupled. A flexible coupled end suction pump, as in our case here, has the impeller and the motor shaft separated by a flexible coupling. A closed coupled pump has the impeller directly mounted to the motor shaft without any coupling in between. The benefit of using a closed coupled pump is that the alignment of the motor shaft to the impeller is fixed. However, a flexible coupled pump can become misaligned during maintenance. This can create issues if not properly reassembled by trained personnel. End suction pumps are designed such that the incoming water enters the pump through the end in a horizontal manner. The water then changes direction and is discharged vertically, perpendicular to the suction. These pumps are typically installed on a solid base on the floor. An end suction pump is capable of being used in HVAC systems with capacities up to 4,000 GPM and 150 feet of head. In short, the main advantages to using a close-coupled pump is the following. First, it requires less floor space within a plant room for installation. Second and most important, closed-coupled pumps do not need to be aligned. This can be helpful if you have a high-speed application at 3,600 RPM where the alignment tolerances are tight. Split-case pumps are similar to end suction pumps in that they are flexible coupled between the motor and the pump. The assembly, including the motor and pump, is rigidly mounted to a common base plate. Pump suction and discharge are arranged in the horizontal direction and are perpendicular to the shaft. Split-case pumps are available either in single or double suction. To be a single suction pump, the water enters the impeller from only one side. For double suction, the fluid enters the impeller from both sides. Using double suction reduces the risk of hydraulic imbalance. The reduction of hydraulic imbalance is one of the reasons why double suction split-case pumps are preferred over single suction. Split-case pumps may have one impeller for single-stage operation or may have multiple impellers for multi-stage operation. Multiple impellers provide increased available head within a single pump. Split-case pumps are available as horizontal or vertical split-case. For horizontal split-case pumps, the impeller casing is usually split in the horizontal plane. For vertical split-case pumps, the impeller casing is split in the vertical plane. To have the casing split is an added value to the pump because it allows full access to the impeller for maintenance. Split-case pumps are used mostly in fire protection systems and in the HVAC industry for large capacity systems. Their capacity range is up to 25,000 GPM and 500 feet of head. If you like this video, like, share and subscribe for more future videos.